Okay, let's move on to the next topic, which is the uncertainty relations and angular momentum. We have seen these when we looked at the Stern-Gerlach experiments. And what I'm going to establish now is that all these things, all these uncertainty relations, completely derive again from the fact that we have commutation relation like this. They are all coming from there. The mathematics is a little bit heavier. Maybe this is the heaviest we've done so far. So hang in there, and we're going to try to get this going. So please take your time to understand each step carefully. Okay. So the idea is that we want to understand better what the commutator means. So we know that we can write eigenket that are common to j square and jz, but we cannot write eigenket that are also common to jx and jy. And this is related to the fact that a measurement of jz will give uncertainty on j. So of course this should be jy in here. A measurement on jz will change jy and jx. Well, actually, it's jz works as well. Okay, this uncertainty is built in the commutators, and we are going to look into that now. So the first thing that we need to know is the Schwarz inequality. So this is the Schwarz inequality we have right here. So if you take any two states, the amplitude of one state times the amplitude of the other state, I mean the self amplitude, if you will always be larger than the square of the amplitude of alpha beta. This is extremely important result, and it's an exercise, but I'm going to solve it here. So I'm going to prove it. So let's consider a state alpha plus lambda beta, where lambda is a complex number, and we are computing its modulus, which is simply complex conjugate times the bra times the ket. And of course, we know the modulus is always positive. A modulus is always positive. It's always a square of amplitude. Okay. So we can distribute this term here, and we get, of course, alpha, lambda, and so on and so forth. I'm not going to write it down. I will tell it, but this is what we get. It's pretty elementary. Now we can decide to consider lambda and lambda star as being independent variable, which is always true because lambda and lambda star depend on two numbers, so the real part and the imaginary part. So we really have two independent variables. So we can decide to try to minimize this function here with respect to lambda. So we take the first derivative of this, which is simply going to be equal to alpha lambda plus lambda star b beta beta. And since we minimize, this is equal to 0. So we impose the derivative to be 0. In other words, lambda star must be equal to minus alpha beta over beta beta, which is coming from this term right here. Okay, so now we plug lambda star back into the initial equation. So when we say initial equation, we mean this equation. Okay, and we find that this is to be equal. This is to be larger than 0. Okay, that's what we have established so far. And so what we find is that once we rearrange everything, so once we have rearranged everything, and this is again fairly elementary, we find that indeed the Schwarz relationship is obeyed right here. So that's a good exercise. So the tricky part, of course, is that we need to go into the minimizing this equation right here. Okay. So what is the consequence of this? Well, the consequence is very important. We are going to start by saying that we are going to start with 3 Hermitian operators, and we are going to choose them so that A, B, and C obeys this commutator relation. So it just turns out that we have 3 operators that correspond to that commutator relationship. And now we are going to choose that A. We are going to write the expectation value A for the state psi written in the usual way, and same for B. and these are of course real number. These are expectation value of a Hermitian operator. Remember, Hermitian operators only have real eigenvalues, so the expectation values are obviously also real. Okay, we are going to build now now that we know the expectation value, we're going to introduce two cats, alpha and beta, that are simply written as this. Here, I can always write this. This is just a choice for the demonstration. And we see that this bracket alpha alpha is given by this term, and this comes from the fact that A is Hermitian, and same for beta. But we also remember that this term that I just circled in this term here is nothing else than the uncertainty square. So this is also what we call a standard deviation. So it's half, so it's the expectation value of the square of this difference between the realization of a measurement and its expectation value. So this is the uncertainty. Okay, so we are making good progress. We of course can compute alpha beta here simply by plugging in, or again, the description of A and B. And remember, I can build this bra as simply being A minus A instead of A dagger, since it's a Hermitian operator. And we are going to try to go from there. So just to summarize, what we've just done is get A alpha alpha, beta beta, and alpha beta. And we have to work a little bit harder on this term. So let's see how we can work harder on this term. Okay, now every operator can be written as a real part plus an imaginary part. Okay, we can write that, of course, because we just take, if we remove the Hermitian operator, if we remove the adjunct or add the adjunct, we get automatically the real and imaginary part. I invite you to try to do that with an example if you're not convinced. So if we now, so this is always true, right? We can always write an operator as being half the sum of the operator plus its Hermitian plus half times I of the difference between the operator, like here. You can always write that for every operator. Now the good thing is that because of this choice of F and G, both of them are Hermitian. I mean, F, you see directly it's Hermitian, and G, you can convince yourself it's Hermitian as well fairly easily, because G dagger is equal to minus I, so it's plus I, times O dagger minus O, which is obviously minus I O minus O dagger, which is equal to J. So we do indeed have a Hermitian operator. All right, so now let's pick an operator O that's obtained from this product. Now we can calculate O minus O adjunct, O dagger, and when we do that, we end up with A minus B equal to IC. Okay, so let's try to see this. So O minus O dagger would be simply equal, I mean, if you calculate everything, you will indeed find that it's A minus B. And in this case, what you get is that the term that we have obtained so far is obtained simply by I times C, so O minus O dagger. So this is, in other words, we can get to the imaginary part of the O operator. And if we go back to the previous slide, we wrote that alpha beta square was equal to the expectation value square of the operator O, turns out. So now I can write this, that the expectation value will be, I can separate the O operator in its two components, the real component and the complex component. And what we find is that when we write that, we can write the F part and the C part, so in this case C is equal to G, okay, and we end up with this expression, which of course tells us that we end up with the modulus of a complex number like this is simply given by this expression. And of course this is always larger than the expectation value of C, and it makes sense because this is a positive number, so therefore the total thing is certainly larger than one component of them. Okay, so this one I think it's important to go back and try to think a little bit about it. The important part here is that the G value I use right here is the same as the C value coming from the commutator. So I think it's important for you to check that. Okay, so we're making progress. Okay, if we put everything back together, we just established this, that alpha beta is larger than C squared over 4, and we also establish that alpha beta beta is larger than this. This is equal to delta A square. This is equal to delta B square, so the uncertainty square. This is larger than alpha beta square, but alpha beta square is itself larger than C square over 4. This is a very important result, because if I take the square root on both sides, and because we have only positive number, delta A, delta B, and so on, and the absolute value of C are positive number, we find this extremely important result. It says that if I do have 3 operators such that A, B is equal to IC, then the uncertainty of A times the uncertainty of B will always be larger than the absolute value of the expectation value of C divided by 2. Of course, this is calculated for a given state. We have used psi in our case. So this is the important result we have. In fact, this is the usual result that people show everywhere when they talk about Heisenberg uncertainty. We're going to see a couple of examples of that now. The reason why I introduce this is, of course, that we know some example of operator that do just that. So one example, Jx Jy equal I h bar jz, is a perfect example of the ABC operator. So remember, we wrote AB equal IC, right? A, B, and C have to be Hermitian, which is fine because Jx, Jy, and Jz are Hermitian, so we are in good shape. And so what it says is that the uncertainty on Jx times the uncertainty on Jy should be larger or equal to the absolute value of the expectation value of Jz divided by 2. Okay, there is a h bar term that comes in front because the C would be my C operator, h bar Jz. So I end up with this relationship here. So if you, for example, if we have a spin 1/2 with a well-defined value of Jz, so that would be a state that coming out of a Stern-Gerlach Z apparatus in one of the 2 channels, let's say the positive channel, then the expectation value of an eigenstate is the eigenvalue itself, h bar over 2. That means that the right-hand side would be equal to h bar square over 4. So that means that there is an uncertainty on both Jx and Jy. Jx and Jy must be strictly larger than 0. So there is indeed an uncertainty of the measurement of Jx. So, in other words, the fact that I know Jz so well, that I know the expectation value of Jz, will change the measurement of SGX. There is automatically an uncertainty. I cannot have delta Jx equal to 0. It's impossible. If I make a measurement of Jz, I cannot have an uncertainty equal to 0 for Jx. Now, if I do take a random state, we also have calculated, so we do not go through SJZ, and we have calculated that the expectation value of JZ will be equally contributed equally from minus h bar over 2 and h bar over 2. So the absolute value of the expectation value of JZ for such state would be 0. And in that case, my uncertainty on Jx can also be 0. And in fact, it can be exactly 0 if I go through an SJX experiment from that. So you see, we can understand all the Stern-Gerlach experiment now based solely on the fact that we have this commutation relationship for Jx and Jy. I cannot resist to show you the other example that everybody knows about, is the fact that if you take the two operator of position and momentum, we can also show that x and px are equal to ai ih bar. So there is commutation. They do not commute though, so the position and the momentum do not commute. And on the right hand side I actually have an operator that's proportional to the identity operator. And in that case we find that the expectation value, of course, of C will be equal to h bar. I mean, C in this case is C in my case is h bar times the identity, and so the expectation value of C is obviously h bar. So over 2 is h bar over 2, and so in other words, the uncertainty on x times the uncertainty of px is equal. It would be larger than h bar over 2. This is the Heisenberg uncertainty principle that you know. I'm going to go back to the spin 1/2 problem with all the knowledge we have obtained so far. So we have quite a bit of knowledge. So first of all, instead of using J and JZ and so on and so forth, we're going to use the notation S, which is simply for the spin. It doesn't make any difference. It's just that we're changing the notation. Everything is still true. We are going to use, instead of using the small j for the eigenvalue of s squared, we're going to use s. But again, this is just notation issue. So for a spin 1/2 system, so when we say spin 1/2, we mean the value of s for the square of the total momentum is 1/2. We have two possibilities, going from minus 1/2 to plus 1/2 in integer steps, so minus 1/2 and plus half. So we're going to know these states 1/2, 1/2, and 1/2 minus 1/2 simply using this notation of the ket. So these are the states we've seen so far, the plus z and minus z state. So what we like to know is what are the matrix representation of Sx, Sy, and Sz. Well, the Sz one is the easy part. We've encountered it a number of times so far. And if we go back to our notation for the matrix element, we end up with this description. And obviously only those states that those diagonal element will be non-zero, because we are working in the basis of eigenstate of Sz. So this is fairly easy. In fact, the eigenvalues are directly are directly to be found on the diagonal part, so h bar over 2 and minus h bar over 2. So what is not so easy is Sx and Sy, but it's actually not that hard either. So to do that, we are going to go back to our favorite raising and lowering operator, s plus minus, and we are going to try to calculate the matrix element of s plus and s minus. So again, the way we do it is like this. If we try to increase the momentum of the plus z state, we cannot, because the plus z state is the maximum momentum value of m, so that would give us 0. But we can increase the eigenvalue of the minus z state, and in fact, if we do that, we end up with this formula, and this is the formula where you want to remember. You remember it's square root of s times s plus 1 minus m times m minus 1. So s is 1/2, m is minus 1/2, and you see that this number here, the square root in front of it, is simply equal to 1. And so we end up with h bar 1/2, 1/2. So remember, s plus has increased its value by 1. This is what it's doing. So the matrix element minus z plus z will be equal to h bar. And this only element that will be non-zero will be this term here, because S plus is going to increase this value by 1, so we end up with plus z times h bar. All the others, this term is going to be increased by 1, therefore the new state will be normal to this state. Same for this one, is going to be 0 because we cannot increase this one. And then when we increase this one, minus z, we get plus z, and minus z plus z will be equal to 0. So the S plus will be h bar 0 1 0 0, and S minus, we can do the same exercise, or we can remember that S minus is actually the complex conjugate of S plus. So we just take the transpose, since S plus is real, and we get S minus. Now things get very easy to get Sx and Sy, because as we know, S plus is simply Sx plus I Sy, S minus is Sx minus I Sy, and we of course automatically get Sx and Sy from solving this very simple equation, and we end up with the value of Sx and Sy like this. Okay, so this is what we end up with. So those three matrices that we obtain in the SZ basis, and we know it's SZ basis because the SZ representation is diagonal, with those three matrices, and it's a 2 by 2 because we only have two possible states, plus half and minus 1/2. And those three matrices are called the Pauli matrices. So we were able to derive all those Pauli matrices simply from the commutator relationship. That's what we've been doing over the past 2 or 3 times that we met. So these are the Pauli matrices. Now we can work out what the eigenstate of a general spin state that's not necessarily aligned with Sx and Y and Sz. In this case, what we are trying to solve is really this problem right here, where h bar over 2 is written, the 2 is written just to make it easier to get the mu. I am not going to solve it in detail because it is really a classical eigenvalue problem. Once you've written the matrix that you need to diagonalize, which is this one right here, you end up with a system that's actually fairly typical that you have solved many times over. In fact, it's a 2 by 2, so the an eigenvalue problem for a 2 by 2 matrix is quite trivial for you at this point. But the point is that, of course, we find mu equal plus or minus 1. Remember, I use mu times h bar over 2, so of course the eigenvalues are still h bar over 2 and minus h bar over 2, which makes sense, of course. This is the only possible realization of the projection of the angular momentum as we found for z. In fact, we never said z was a kind of arbitrary direction, so of course for the general direction n, the eigenvalue will be the same. Now for the eigenvectors, again, I have all the details on this slide, but I do not wish to go into detail simply because this is again, this is not a physics problem, it's a simple math problem that you can solve. We end up with the general n and minus n state, and when we use the right angle, so for example phi equals 0 for the plus x state and phi equals pi over 2 for the plus y state, we end up to exactly the same state that we've been looking at since the beginning of those lectures. So it's not a bad idea to remember maybe those two states right here, plus n and minus n. It can be very useful for your sanity check. Okay. So one thing that we can do is to determine the matrix representation for Sx using the spin 3/2 states as a basis. The way to do it again is to compute Sz, and then to compute as well S plus and S minus, and we will be doing that in class. The thing is, you have to remember, because you have a spin 3/2, you really have 4 possible states: minus 3/2, minus 1/2, plus 1/2, plus 3/2. So your matrices become a little bit more complicated. They are 4 by 4 instead of 2 by 2, but the S plus, S minus have mostly zeros, and this is where we are going from there. Okay, now we can think about the last example in this chapter, which be the Stern-Gerlach with spin 1 particles. So remember, we had only 2 possibilities with the spin 1/2. We had silver atoms that have just a single electron on the outer shell, I mean the S state. Now suppose that we have prepared a system with that have a spin 1 particle. In that case, of course, the three possible realization of Jz are h bar 0 and minus h bar, since m can go from minus j to j and j equal to, so j equal to 1, so m is minus 1 plus 1 and 0. So in unit of momentum, it's h bar 0 and minus h bar. And the notation we use in this case is, of course, the same as we've done before. So the first number is simply the total spins, it's 1, and the second number is the projection. And we have added a z here simply to say that what we are looking at is the eigenvalue of Jz. We don't always do that, but we sometimes have to do that, especially when we want to mix with another, well, I mean, when we want to study another component. And this is exactly what we do here. So what we are going to do is to take the output of an SGY experiment, and we want to know, and we are going to pick the 1, 1, so all those electrons that have, all those particles, sorry, that have a plus h bar projection along the y direction. So it's this states right here. And what we're interested in is how many of those will be deflected as plus h bar, how many will be deflected as if they were minus h bar for the momentum, and how many of them will not be deflected. And those who will not be deflected correspond to m equals 0. So what we really need to know is what is the probability amplitude here, which is simply saying what's the portion, so the square of this, the square modulus of this number will tell us how many particles come through this channel. So for that, we need to calculate this bracket, and both elements have to be calculated in the same basis. So clearly this one is written in the SY basis, this one is written in the SZ basis. So we're going to work everything in the SZ basis just to make things easy. We have actually calculated SY before. In fact, we have not calculated it, we have obtained that as an example I showed you. That SY can be obtained by this matrix representation. We have seen that, but I strongly advise that you calculate this SY using the S plus and S minus. This is fairly straightforward to do, but this is one of the examples that you should be able to do yourself. Now, once you have this matrix, we can calculate the different eigenvectors. In particular, we can calculate the eigenvector that correspond to the matrix, to the eigenvalue plus 1. This is the one we're interested in. And what we do when we do that, we have to solve a problem that, this again, an eigenvalue problem, a 3x3 system. Again, this should be trivial for you at this point. And we obtain this particular state 1, 1, which is given by those, it's normalized, so it's what we need in order to have the right number of particles. And what we find when we do this is that the projection that we were interested in, which is here, and we drop the z because this is supposed to be the z representation, is 1/4. So the Stern-Gerlach experiment, in this case, show that we do not have an even distribution of deflection. We have only 1/4 that get deflected here, and you can calculate that this number is also 1/4 for minus h bar, and the rest is not deflected. So you know we have an asymmetry between the deflection. Half the particle are not deflected, and the other half is deflected with an equal number deflected upward, and the other number deflected downward.